Okay, so my name is Henry. I'm a PhD student at U of T. So to give you some context, I work in the galactic astrophysics. So that my research is about the Milky Way galaxy. So that my work mostly about try to get as much as you can from stars in our galaxy in order to understand our own galaxy. So here is just one slide of motivation. So as the title said, our motivation is to build a foundation model for star. So what foundation model usually means is that foundation model is just a neural network that trains on most available data at scale. And then you can fine tune this foundation model for downstream tasks later. And one of the characteristics of transformer is that you can build really flexible model with it. So what I mean by that is that if you want to build an AI in the future, you would want to have a neural network that you can give any data. For example, in this work, what you have known about a star to this neural network, and then later you can request for information. For example, what is the unmeasured quantity about that particular star? And because transformer can give you really flexible input and output, it means that you can really achieve your goal of training with most available data set because the flexibility in the input and output. So it means that you can really train with really heterogeneous data set at scale. So just in case you're an astrophysicist that have never looked onto the night sky, you can have a star in the northern hemisphere that can only be observed by telescope in the northern hemisphere, but not by telescope in the southern hemisphere, and vice versa for a star in the southern hemisphere that can only observe by telescope in southern hemisphere. So in the past, if you don't have flexibility in input and output, you may need to train two different models in order to get whatever information you want from the star. But with transformer, it's actually possible to just train with all the data that you have at once. So here is just one slide of our model and data. So it just in this work, it's just a small proof of concept model. So our model is based on transformer encoder decoder architecture. So it's based on some early work from language model on a question and answering system, where in language model you give the context, and then you give the question, and then you want the model to answer your question. But in our scenario, we want the model that we can give any data that we have about a star, and then we request for information, so that you have in this model you have an encoder, so that you can give what data that you have about a star, which is the list of data name, because the model needs to know what is being given, and the list of corresponding values, and then you give it, the encoder will encode whatever is being given to a context of a star. So it's very much like in language model, you have a sentence context, but in this scenario, you have a star context. And the decoder will take in the output from the encoder. And as an astronomer, you can request for information, and the decoder will figure it out and then give you the answer. So one important thing you have to understand here is that the embedding, so the data is embedded by their name along with their corresponding value. So much like language model, the data name will be converted to a vector, and the vector will multiply with the magnitude of the data, and will give you the final embedding. And that's what we meant by a nonlinear embedding. So in our small proof of concept, we only mostly use Gaia XP spectra, which are very low resolution optical spectra and precise stellar parameter from apogee and 2-mass photometry. So here is an example for our model, because we have one thing that we want to do is that can we give Gaia XP spectra, and then we request for stellar parameter. So in this case, it's basically in traditional sense, it's a discriminative task. So there are many work on this. So mostly the state of the art to get stellar parameter from Gaia XP spectra is using XGBoost. So in this panel, we show the performance on expertly trained XGBoost, and we also show the performance of our neural network, which don't actually fine tune with this task. It's just coming out of the box. So you can see our neural network actually outperformed the XGBoost by a little bit, even though our model don't even fine tune with this particular task. And you can see that our model actually also gives you a reasonable uncertainty, where data with the most discrepancy to the ground truth also have the highest uncertainty. So here's another example. Because we have flexibility in the input, so we can actually try to randomize the spectra. So because you can randomize all the pixels of the spectra, but the information content is exactly the same. So you should expect the neural network still works well, even though you shuffle the input. So in this panel, we show that the neural network performance where after we shuffle the input spectra randomly for each star, and you can see that our model still managed to predict surface temperature fairly well. And in the middle panel, we deliberately took out the most informative part of the spectra so that we want to test if the model failed at this task, because we expect it to fail because we took out the most informative part. And as you can see here, our model actually failed to do this task as expected. But the model also gives you a reasonable uncertainty where it tells you that, yeah, you can trust none of this prediction. And in this panel, we give the most uninformative part of the spectrum, but we mix in the surface temperature randomly in the input. And because the surface temperature already is being given in the input, so when we request for surface temperature, you expect that the model will just give you the surface temperature. And expected, like as expected, the model actually predicts surface temperature perfectly because it's already in the input. But you don't have to do discriminative tasks because, again, because of the flexibility in the input and output. You can actually do generative tasks where in this panel, you can just give stellar parameters, for example, like surface temperature, surface gravity, metallicity, and then you ask the model to generate the XP spectra. And again, like you don't have to do anything to the model will just work out of the box. So here we show that we try to make it to generate a red giant spectra, but with different metallicity, and you can see that our model correctly generates spectra, but also shows sensitivity of metal line as expected, which is great. And we can also give a portion of Gaia spectra, which we can give the first portion, and then we ask the model to generate the next portion, or we can give the model the second portion and then generate the first portion. And you can see the model works quite well here. And we can also try to do some fancy stuff as an astronomer, because the model knows how to generate spectra, so that you can kind of try to generate spectra at different with different extinction, but with the same intrinsic stellar parameter, and then you can try to calculate the extinction curve yourself. As you can see here, the black line is the calculated extinction curve from the model, and the colored line is the extinction curve with different parameter. And you can see that our model actually learned the extinction curve by itself, even though we never really fine-tuned this model to do this particular task. And here's another generative task. So one fancy thing you can do is that you can try to generate isochrone by sampling surface gravity and metallicity. And you can see here is the training data. So the y-axis is the surface gravity, x-axis is the surface temperature, and you can see that red giant, and you can see main sequence. What we do here is that we only give surface gravity, but we request from the model the surface temperature and luminosity. As you can see, our model actually managed to produce roughly the right surface temperature and luminosity to recreate the training sample. So here's one thing about how we treat the embedding in our model is that because when we request for information, we train the decoder such that when you give the embedding of the data to the decoder will predict the corresponding magnitude. So it means that you don't have to give every single data. You don't have to request for every single data during training. So, for example, we withheld the Gaia BP LP color during training, so that we never request Gaia BP LP color during training from the decoder. But during testing, we want to see if the model will still manage to produce BP LP color, even though we have never really trained it before for the decoder. As you can see here, our model actually still managed to predict BPRP color, even though it has never seen it during training for the decoder. But the encoder have seen it during training. And also gives you a reasonable uncertainty. So that's great. It means that our embedding is meaningful because the model still managed to do it. So here is one slide about obviously reliability issue that this kind of very flexible model, they always have reliability issue. So you can do some, there's some interesting scenario where you give it a very ambiguous questions. Like for example here, you give the model the surface temperature of a star of 4,000 degrees, and then you request what should be the surface gravity of this star. And as a human, you can just look at the training set, and here is the line for star of 4,000 degrees. And as you can see that like you can have a red giant star that has surface temperature of 4,000 degrees, or you can have a main sequence star also with a surface temperature of 4,000 degrees, and both have very different surface gravity. And if you actually do it with our model, the model will just tell you about like something like log G is equal to like about 3.0 dex, but the uncertainty is about 2.0, so that it basically just very highly uncertain, which is right because it's not too ambiguous, this question. But now if you do it with the same question and you give it the model a additional condition that this star has no extinction, and as a theoretical physicist, you probably say that, oh yeah, this extinction has nothing to do with surface gravity, so that the model should still tells you this is very uncertain. But for an observational astronomer, it probably would tell you that, oh, if a star has no extinction, and the star should probably be main sequence, because star with no extinction always associated with a star that is very close to us. In order to observe those stars very close to us, there must be main sequence, otherwise they will be too bright for the telescope. And our model behaves like observational astronomer, that the test tells you that this star is a main sequence with very high certainty. So that means that this model is quite literally like just machine learning, but not quite AI, because like if you want to build AI, like you actually want it to behave like a theoretical physicist. So here's just two work in progress with Josh Spiegel, that now we will try to predict the full PDF instead of a number with uncertainty. So that now we have a model that can actually tell you that we did the same exercise from the previous slide, and it just tells you that, oh yeah, you can have a red giant and main sequence. And also shout out to Lowland chat Gaia, that now we also have a natural language interface. We can communicate with this very flexible model. For example, here I just showed that ask ChatGPT to compare the XP spectra of two stars with different surface gravity, and because I can show ChatGPT how to use our very flexible model, and then GPT will just know how to use it. And here is a conclusion that we adopt the same technology behind LLM to floating point data. And just a proof of concept, and to show that there is a possibility of large astronomy model in the future. So thank you.
Do we have any questions for Henry?
Yeah, very nice talk. What's the size of the embedding space, just to get a sense of?
So the embedding space has dimension of 128 dimension. Yeah.
Adrian, any questions on Slack?
So if they finish typing quickly, then yeah.
Well, in the meantime, we can go to the Paris node.
Are there any questions here? No. Yeah, there's Nabila who's got a question.
Thank you. I was wondering whether there is any validation of the data that you input in your training. I mean, you put all the data known, or is there any cleaning, selection, understanding of possible biases?
Okay, yes. Okay, yes. So as a proof of concept, because we only want to do a small model that just try to make a point, so that we only do stars that exist observed by the SDSS Apogee survey. But in reality, it doesn't really matter, because the whole point of this is that you can train with most available data set that you have, because of flexibility in the input and output. So that in the end, you probably will, if you want to build your ultimate foundation model, you probably will actually just want to dump all the data that you have to the model.
Did the person finish typing?
As soon as I called them out.
I see. Any other questions here? Otherwise, let's thank Henry again.
Thanks.